we'll be solving two improper integrals of type 1. Here's the first one. I have minus infinity here. That means I need to replace that by t and take a limit. So this is going to be t. I'm going to have minus 5, 1, 2x plus 1 to the 4 as t goes to minus infinity. At this point, I can use any technique I want. I'm going to use substitution. I'm going to replace this by a new variable. So I'm going to take u to be 2x plus 1. Du will be 2dx. So I'm going to end up that's going to give me 1/2 du as my dx, 1 over u to the 4 instead of this. Now, whenever you change your integrals, your variable in an integral, whenever you do substitution, you need to change your bounds as well. These are the bounds for x. I want to get the bounds for u, so I'm going to take minus 5 and I'm going to take t and plug it into this. So I'm going to get, at t, I'm going to get 2t plus 1. At minus 5, I'm going to get 2 times minus 5 plus 1. That's minus 9. So I'm getting the limit as t goes to minus infinity. 1/2 u to the minus 4 plus 1, so minus 3 over minus 3, from 2t plus 1 to minus 9. I'm going to get minus 1/6, 1 over this one first, so minus 9 cubed. And then I'm going to plug in 2t plus 1. I'm going to get minus 1 over 6. And then I'm going to get 1 over 2t plus 1 cubed. And I'm going to need to take the limit of all of this. That term doesn't have a t, so it just stays the same. So I'm going to get 1 over, I have 6. Actually, I've computed it before. I have 6 times 9 cubed. That's 4,374. So 4,374. For this one, I get plus 1 over 6, 1 over minus infinity cubed. That goes to 0, so I get 1 over 4,374. So I've done one example where the top bound was infinity, one example where the bottom bound is minus infinity. Now let's do an example where both are infinite, just to show you how to split. So let's look at the integral from minus infinity to plus infinity, 1 over x squared plus 1 dx. Since both bounds are infinite, I need to check each of them separately. I'm going to split somewhere in the middle. You can pick any a you want. It doesn't matter. They'll cancel out in the end. You don't need to go crazy either. In this case, a equals 0 is perfectly adequate, but anything would work. It just needs to be a finite number. So here I'm going to look at the integral from 0 to positive infinity. I'll compute this limit. If it gives me a finite number, I'm going to compute the second one. If that also gives me a finite number, the answer will be the sum of these two numbers. Now it's tempting just to write that this is arctan and plug in infinity, but of course FTC only works on finite intervals, so I'm going to have to first replace infinity by t and add a limit in front. So now I'm going to get limit as t goes to positive infinity. Now I can use FTC and say that this is arctan of t from 0, arctan of x from 0 to t. And then I'm going to plug in the top bound first, subtract what I get by plugging in the bottom bound. Now this is the moment where choosing 0 is nice because you can actually evaluate that. Otherwise you'll be left with some arctan that you cannot evaluate. And then I have a limit of arctan of t. If you remember the graph of arctan, excellent. If you don't, here's a review. It has two horizontal asymptote at pi on 2 and minus pi on 2. So if I go to positive infinity, I get pi on 2. So I get that the first interval from 0 to infinity, the first integral from 0 to infinity gives me pi on 2. So that half converged. Let's look at the second half. The work is almost the same, it's just at the end the limit is different because it's really the same integral you're computing. This is the point where it starts being different. I'm going to get 0 first, minus arctan of t, and then this limit now this limit, if I plug in minus infinity, I'll get minus arctan of minus infinity. Let me put brackets around it. And now I'm going on this side of the graph. So if I'm going to minus infinity, the height is going to minus pi on 2. So this would be minus pi on 2, which ends up being pi on 2 as well. So both halves of these integral give me pi on 2. If I want the whole thing, I'm going to have to add them up. This one we said was pi on 2. This one is pi on 2 as well, so the whole integral is pi. Before we stop, let's just get back to the geometry picture. One over 1 plus x squared has a maximum of 1 at 0, and then it tapers down on either side. What we did is, instead of looking at that area at once, we divided it into two parts. We made sure first that this half actually converges despite the fact that I have an unbounded region. This area we proved was pi on 2. Then we looked at the second half and proved that this area is pi on 2 as well. And it makes sense if you look at the picture, they're really symmetrical, so it makes sense that you get the same thing, and we just proved that the whole area is pi. Before we stop, let me say the reason we split it into two halves is we want to avoid a situation where both parts would be infinite, but they'd be canceling. So if you compute it at once, you'll get, let's say, 0, the two would cancel, but each part is infinite. So really what you're getting is infinity minus infinity, which should not give you 0. We can't compute that if they're areas.